Welcome to section 7.4. Today we're going to work on the inverse Laplace machine. So let me remind you of the derivative formulas. These are, I believe, 19 and 20 in your table. L of y prime is s big Y minus y of 0. And L of y double prime is s squared big Y minus s y of 0 minus y prime of 0. Now, in your table, those are stated in terms of f, not y. And let me show you just an easy example of how the whole process is going to work with an example that we could have done, solve y prime equals 2y, y of 0 equals 3. We could do that separation of variables or linear and finding an integrating factor. But let me show you how it works here. We sent this equation through the Laplace machine. So we take L of both sides. L of y prime is s big Y minus y of 0, which is 3. And then L of 2 little y is 2 big Y. Then we solve for y. And now we're ready to run it through the inverse Laplace machine. L inverse of 1 over s minus 2 is by formula 3 e to the 2t, and then this 3 is just a constant, so it carries along. And so we have a solution to the whole problem. And what I want to point out here is that when you solve an initial value problem with Laplace transforms, the initial condition is built into the answer. When you're done, there's nothing left to do. Whereas if we had solved this by separation of variables or by the linear integrating factor, e to the integral of p dt, the last step, after we got our general solution, step 5 would be to plug in the initial condition and solve for the constant. So you don't have to do that when you're using Laplace transforms. Okay, so let's talk a little bit more about inverse Laplace transforms. We looked at this in the last lecture a little bit at the end. What we're going to be doing is reading the table backwards. So since the table tells us that L of 1 is 1 over s, that's the first formula in your table, then you could say, if you read that backwards, that would read L inverse of 1 over s is 1. Same with L of t squared versus L inverse of 2 over t cubed. And then finally, I gave an exponential example using formula 3. So usually it's not going to work out like this, where you have the perfect expression to take L inverse. You're going to have to do a little multiplying or dividing by constants. So let me show you what I mean. If we look at this first formula, so I'm putting equals here, but I'm not ready to write down the answer. It's closest to formula 2 with n equal 3. So if we just look at what L of t cubed is, using formula, I'm not using 3, I'm using number 4. This is, wait a minute, hang on. No, I'm good. This is number 2. L of t cubed is going to be 3 factorial over s to the 4th, which is 6 over s to the 4th. Well, I don't want that. I want 3 over s to the 4th. So since half of 6 is 3, I'm going to go 1/2 t cubed. And that's my inverse Laplace transform. And you could check it. I mean, you could check it in your head, but L of 1/2 t cubed is 1/2, excuse me, times 3 factorial, which is 6, over s to the 4th, which is 3 over s to the 4th. Okay, next one looks closest to formula. If you have your table in front of you, I have an abbreviated table on the next page, but there's an s squared plus 7, but no s on top. So that's closest to formula 6 with b equal root 7. So this is closest to 6, b equal root 7. So if we just took L of sine root 7t, we'd have a root 7 on top, and then s squared plus 7 on the bottom, we don't have a root 7 on the top, so we'll just take 1 over root 7 sine root 7t. Now, a lot of this this stuff here, you could do this in your head. Now, at first, it might not be so easy, but eventually, you know, if you were just on a test to write down L inverse of this is this, I would understand that you were doing this process in your head. And your book has a slightly different way of doing it. They would write this as, they'd say, okay, this is L inverse of, if I want to use formula 6, I'm going to have a root 7 here, and then a s squared plus 7 here, and then I don't have a root 7 on top, so here I'll put 1 over root 7, okay, and then they'll pull out the 1 over root 7, and then take L inverse of this using formula 6, so get the same thing. It's just whether you want to write it down formally or like this. But this is helpful too. Sometimes I'll do it like that. Okay, next one. If the coefficient of S is not 1, then you're kind of in trouble because all the formulas in your table have the coefficient of S equaling 1. But nonetheless, this is closest to number 4. So what we're going to do is get rid of that 3. So this is L inverse of 1 over, we need to pull the 3 out. 3 squared is 9. And so then I'm left with S minus, I pulled a 3 out, but there's no 3 in 2. So S minus 2/3 quantity squared. Okay, so now the 1/9 is a constant, and I can use formula 4. This is number 4 with A equal 2/3. And again, 1/9 is a constant. So this is 1/9 t e to the 2/3 t. I've got a sad face by the the inverse Laplace man, basically because it's the inverse of happy face, but also because it does take a little bit of work to do the inverse Laplace transforms. It's a little bit of sleuthing. Okay, next one. We're going to have to complete the square on this to make it look like something in the table. And so I have CS, it's complete the square. First thing I need to do, when you complete the square, you need to get rid of the coefficient, again, of S. So pull that out. This is 3 over twice S squared plus 4S plus 5. Which is, now I'm going to complete the square, 3 over 2, and then, actually, I'm going to take that 2, sorry, erase that. This is 3/2 over, so I'm taking that 2 in the denominator, putting it upstairs, 3/2, and now I'm going to complete the square on S squared plus 4S plus 5, and this is how I do it. I look at the middle guy. What could I put here? So when I FOIL this out, I'll have a 4 in the middle. Well, there's only one number that's going to work, and it's 2. Okay, and then I do my correction factor. When I FOIL this out, I'll get S squared plus 4S plus 4. I have S squared plus 4S plus 5. So I need to add 1. Piece of cake. So now what we want is L inverse of that. S plus 2 quantity squared plus 1. Okay, looking at my table, I'm thinking number 8, because there's no S on the top, and my A is -2, and my B is 1, and that 3/2 is a constant. I can just pull it out. So this is going to be 3/2 e to the -2t cosine, no, using formula 8, sine of t. All right. So we're going to be doing a lot of partial fractions today. The next, well, we're doing one more complete the square, and then I'm going to do a bunch of partial fraction ones with you. So it might be a long lecture, sorry. So this is complete the square and use 8 and 9. This is a very, very common thing to have to do this. So here we go. I want L inverse. I'm just going to go ahead and complete the square because it's super easy. S plus 3 over S. Okay, what can I put here so that when I FOIL this out, I'll have a 2s. Well, there's only one number that'll work. It's s plus 1, quantity squared. But when I FOIL that out, I'll get s squared plus 2s plus 1. I want plus 10, so I need 9 more. Okay, now I'm going to separate this out into 2 fractions. Because if you look at formulas 8 and 9, number 9, if you have an s minus a squared downstairs, you need an s minus a upstairs to match with it. So what I need is an s plus 1 on top, not an s plus 3. Fine, I'll put an s plus 1. S plus 1 squared plus 9. Now, I need to add on another fraction so that when I add the 2 together, I'll have s plus 3 upstairs. So leave the denominator the same. And then I wanted s plus 3. I have s plus 1, so I need to add on 2 more. Okay. Now, this first guy is number 9 with a equal -1 and b equal 3. So that's going to be e to the negative t cosine of 3t. And then this next guy is going to be formula 8 with the same parameters. A is -1, B is 3. Now, I need for formula 8 to have a 3 upstairs. I have a 2 upstairs. So this is going to be 2/3 e to the negative t sine 3t. And let me just explain to you how I did that in my head. I thought of this as I wanted a 3 upstairs, so I put 1 in my head. You could actually write it down too. S plus 1 squared plus 9. Okay, I needed a 3 upstairs, but I had a 2 upstairs. So the 2 I'm moving off to the side, and then I can't just go around multiplying things by 3 without dividing by 3. So that's how I'm thinking of 2 over this. I'm thinking of it as 2/3 times 3 over this. And so that's where that 2/3 here came from. You guys are pretty sharp, so I'm sure you're following along, but it's a little tricky at first. Okay, now we get into partial fraction stuff. When something doesn't seem to be matching up with your table, you can try completing the square. Let's see, that's not going to help us here. It's going to be easier to just do partial fractions. So I'm going to do partial fractions on PF on 1 over, we need to factor this completely, s times s squared plus 3. No, that's a 2, so it would be s plus 3. Sorry about that. And that's going to be a over s plus b over s plus 3. Now, if you've forgotten your partial fraction decomposition rules, I put a abbreviated table from my last class, the 1B class here, and there's a bunch of examples on how to treat linear factors, irreducible quadratics, and then repeat linear. So if you have x plus 1 quantity squared, you won't get repeat quadratics. It can happen, but it won't happen to us. I'm not that cruel. Okay, so next step is to clear the fractions. So multiply both sides by the denominator s times s plus 3, and that gives us 1 equals a times s plus 3 plus b times s. And then we pick some values of s. I'm going to go s equals 0 to get a. That gives me 1 equals 3a. So now I know a is a third. And then s equal -3 will give me b, because I'll have 1 equals -3b. So b is -1/3. Okay, so what I have is L inverse, going down here, I'll put it here, L inverse of a over s. So a is a third, so 1/3 over s, and then plus b, but b is negative, so minus a third over s plus 3. So now I'm using formulas 1 and 3 from my table. This is 1/3, because L of a third is, what am I trying to say? L, back to our table. L of 1 is 1 over s. So think of this as 1/3 times 1 over s. So this is 1/3. I probably made that way more confusing than it had to be. And then minus 1/3 e to the -3t. Okay. 2 more partial fractions with you. I'm trying to do like one of each type. So this is s cubed. It's pretty small, but it's s cubed plus 4s. So I want partial fractions on s cubed plus 4s. So I go 1 over, pull out as much as you can, s times s squared plus 4. Now what I have is a linear and an irreducible quadratic. So the linear gets a constant on top, and the irreducible quadratic, s squared plus 4, gets a linear on top, bs plus c. Okay, now I clear my fractions, multiply both sides by the denominator on the left, and I get 1 is a times s squared plus 4 plus bs plus c times s. Okay, so I'm going to start with the low-hanging fruit. S is 0. That gives me 1 equals 4s. 4a, sorry. So a is a quarter. Okay, now there are no values I can do to just wipe out b and keep c, or wipe out c and keep b. So I'm just going to pick 2 more values, and I'm going to make them small to make my life easy. So I'll start with s equal 1, and that gives me 1 equal 5 times a, but a is a quarter, so 5 quarters plus b plus c. So the best I can do, I'm just going to solve this for b plus c. You'll see why in a minute. B plus c is -1/4. Now I'm going to let s equal -1. That's a small number. You could let s equal 2, 3, 4. It doesn't matter. You just, if you pick small numbers, your system of equations is going to be easier at the end. So this gives me 1 equal, again, 5 quarters. And now it's going to be s is -1. So -b plus c times -1. So negative gives me positive b, and then minus c. You can pause the video and make sure you understand that, or get the same thing if you try and do it. So now I get b minus c is also -1/4. So now I have a system of equations, and I can solve them. I could substitute. I could solve this one for b and plug it into this one, but I'm going to do the elimination method. I'm going to add these 2 equations together. 2b is -1/2. So b is -1/4. Now to get c, I go back to either one of those equations and plug in b, and that gives me c equals 0. All right, so now we're ready to take L inverse. L inverse of a over s. A was a quarter, so 1/4 over s, and then c was 0, so it would be minus 1/4 s over s squared plus 4. You could do plus and then put your minus upstairs, but I'm going to write it like this. Okay, so s over s squared plus 4, this is going to be formula, I'm looking at my table, 7. So this is number 7 with b equal 2. Okay, and so I just think of that 1/4 as a constant, pull it to the side. An L inverse of s over s squared plus 4 is cos s over s squared plus 4 cos 2t. So this is going to be 1/4 over s, L inverse is just 1/4, minus 1/4 cos 2t. All right. One more. This is a repeat linear factor. So again, I'm going to do partial fractions on 2 minus s over s plus 1 quantity squared. And for repeat linear, you have a constant over the linear, and then another constant over, in this case, the linear squared. All right, so clear your fractions. 2 minus s equals a times, we have 1s plus 1 left, and then plus b. If s is, let's go low-hanging fruit, -1, then we get 3 equals b. All right, and if s is next smallest number, let's go with 0, I get 2 equals a plus b, but b is 3, so a is -1. So what I want is L inverse of a over s plus 1. A is -1. -1 over s plus 1. That's going to be easy. That's formula 3. And the next one is going to be, what was b? 3 plus 3 over s plus 1 squared. So this is number 3, and this is number 4, with a equal -1. And so this is going to be negative e to the negative t plus, 3 is a constant, 3t e to the negative t. You could also use formula 5. I just want to point out to you in your table, 4 is just a special case of 5. 5 is t to the n, e to the at, and so 4 is 5 with n equal 1. All right, so that comes up a lot, so they have a special formula for it, but you could have also used 5 because 5 covers 4. Okay, comment on partial fractions. You need to know how to do all the types I'm doing and all the types in your homework. But just because you need to be able to do it doesn't mean you have to actually do it. So on the instructor tips in some of your homework problems, I have, use technology to get your partial fractions, because there's no reason for you to spend half an hour finding A, B, C, and D if you could do it if you had to, right? So I use the Symbolab partial fraction calculator, and what you do is you just type in partial fractions, just start typing and partial fractions will come up for you, and then the expression. Their default expression is in terms of x, but you can switch it to s if you want to. All right, so here's an example of that, and this is the last one I'm going to do, and then you can do a practice problem for homework and you're done. This is number 13 in your homework. It's stated like this: find L inverse of big F if S big F minus 4 big F is this. So the first thing you want to do is solve for big F. You can't take L inverse of it if you don't know what it is. So there's a big F in both expressions there on the left. So let's factor out a big F, and then we get S minus 4. And that's equal to S plus 3 over S squared plus 8s plus 16 is S plus 4 quantity squared. So big F is s plus 3 over s plus 4 squared times s minus 4. Okay, so I want to take L inverse of both sides to get L inverse of F. Now I could do partial fractions on this and get the right answer without any problem. The decomposition would be A over S plus 4 and then B over S plus 4 quantity squared because it's a repeat linear, and then a C over S minus 4. So it wouldn't take too long. There's only 3 constants. I could do it, but instead I went and typed it into Symbolab and had Symbolab do it. And so let's see how this works. L inverse of big F is going to be L inverse of, now Symbolab is going to not give you complex fractions. So if A is negative 7 over 64, which it is, it's going to put the negative 7 on top and the 64 on the bottom. But when you take L inverse, you want to think of that literally as A on the top. So I'm going to rewrite that as negative 7 over 64 over S plus 4. It's actually easier with a complex fraction. So normally we don't like complex fractions because they can be simplified, but in this case you don't want to simplify them. You want to leave them complex because this is the constant on top as 1 over S plus 4. That's just formula 3 to take L inverse. So plus B evidently is 1/8. And C is 7 over 64. Okay, so I have formula 3. This is number 4. And this is number 3. All right, so this is going to give me negative 7 over 64 e to the negative 4t, and then plus 1/8 t e to the negative 4t plus 7 over 64 e to the 4t. And that's it. So the next one that you're going to do for homework practice and the solutions at the end, my hint is complete the square and then separate into 2 fractions because you're going to end up using formulas 8 and 9. So it's super similar to E. Complete the square, use 8 and 9. Okay, and that's it.